Hi, ladies. Welcome to Wednesday, March 25th. This is the day 3 for us to be working on chapter 3. And it's kind of hard to believe that we've been home and doing long distance learning for almost a week. And seems like things are going pretty much okay. The problems of PowerSchool from last Thursday, our first day, seem to be much better than they were. So hopefully you guys are doing well, and I want to go ahead and get started. I have a lot of things to review with you guys today, things that you've worked on, questions that you asked, and I want to go over the last bit of new material for this chapter. So the outline for today includes prayer, update, going over review questions, prime time, class material, and the wrap up like I've been doing. So let's begin with prayer. Pope has actually, I think earlier today on Tuesday, which is when I'm recording this, declared that he'd like everybody to do an Our Father today together in solidarity, recognizing the world is dealing with and coping with the coronavirus. So if you join me in an Our Father, in the name of the Father, and the Son, and the Holy Spirit, amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen. So, first thing, some more pictures from my last trip. I hope you're kind of enjoying these. No one's really commented on them, but I felt that I wanted to still try to stay a little bit more connected with you. So hopefully you enjoy some of these different pictures. So this one fish is a type of angelfish, and I really don't know what the kind is because I don't remember. This guy down here in the lower left-hand corner is a Moorish idol, and he's got this really big nose like lip things, and you can see quite a few of these in aquariums across the country if you've visited any of them. And this guy is a leaf fish. He's really thin and skinny, and his eye is here, and this is his tail down here, and the rest of him kind of looks like a leaf, and he really is thin. I really struggled trying to get in. There's this big head of coral here and some rocks. I couldn't get a better picture of him. This is as good as I could do. But have not seen many of these because they're really only in the Pacific Ocean. So all of these fish look different than similar fish do to them in the Atlantic Ocean. So these again are from some of our pictures from our trip over Christmas. So an update, homework submission definitely is much better this week than it was last week, but I need your help. So right now, when you submit your homework, if you submit it as individual photos, I have to take each of those photos, download them, open them, and every JPEG that you send actually takes about 2 minutes for me to process. So if you think that you send in maybe 6 photos from last class, that's about 10 minutes worth of downloads, and I have to do that for all 50 of you guys. That's a lot of time. So I'm spending a huge amount of time just basically downloading all of your photos. So if you could help me out, I would really appreciate it if you could put those all in a single document. I know there's a few of you who have emailed me that there's been some issues with that, so I am asking some of your fellow classmates, if any of you are being really successful at submitting your homework using photos and putting them into some type of document, could you send me a quick email and let me know how you're doing it? It would be nice to have some type of instructions out there that we could post and share to try to help people out. So I would appreciate your help with that, because I don't know what's working for you guys and what's not. So it's really hard for me to give guidance on that. So if anybody is willing to either shoot a video with a some type of screenshot or write out some instructions, would greatly appreciate that. So in the future, I'm actually going to combine all your classwork into one listed item on PowerSchool, and it'll be just worth more points if there's a lot of things that you guys did in class. And I'm going to try to request you guys to just send in one document instead of multiple documents. That should save me a lot of time because I spent over 4.5 hours looking at your homework or your classwork from last time, and I'm not done. So it's a huge time sink for me, in addition to all of the other stuff that I'm trying to do to get this video up and running and together. So thank you, ladies. I really do appreciate your help. So from last time, Block 6 had 2 sets of review questions from Maya and Victoria, and here's the answers. So if you're in Block 6, please pause the video and take a look at these answers with your review questions. If there's anything that doesn't make sense, include it in your survey at the end of the day today. Here is the answers to Block 7, and when I noted this, I took a look at number 4, which was looking for the clues that give you an idea if a chemical change has occurred. I'd like to revise something that's in your packet. So if you could, and this pertains to all the blocks, if you could go back and pull out your packet on the page where you were working on this, which I don't have my packet out in front of me. So the page that had all of this information, where we have the 5 clues for the types of changes. This is on bottom of page 8. So a new color appears. Your packet says heat or light is given off. I would like you to change that. Instead of saying heat or light, say smoke or light. And then find bubbles are formed, a solid forms in a liquid, that's good. And then unexpected temperature change is fine. I have found that if we have smoke or light being separate from the temperature change, that's a better way of looking at it. And when we talk about heat being produced or absorbed, that description is actually contained in the temperature change, because if heat is produced, you're going to see the temperature growing up. And if heat is absorbed, then it's going to have the temperature going down. So if you would make those modifications on that page in your packet, that would be a really good idea for looking at your 5 clues of a chemical change. Block 8 didn't have any questions today, so there are no answers to review. So review questions, if you're responsible for these for next class, please email them to me by Thursday at noon, and I will go ahead and get them posted out. Please email the questions without the answers and have the answers listed separately. And for unit conversion problems, write out your work. If you're not sure when you're assigned, you can refer to the email that I sent to everybody over the weekend. Also, I've posted the information on P-Learning. So your prime time today is blue packet, page 14. So this is the page that we skipped in the packet. And it will be kind of important for you to draw some of these pictures in here. So we've got scientists classify matter into one of 3 categories: elements, compounds, and mixtures. So elements contain only one type of atom and cannot be broken down into simpler substances by either physical or chemical means. They can exist as either atoms or molecules. And they show over here in the boxes some pictures as well as some formulas. So these circles are atoms, these triangles are atoms, but these ones that have 2 circles in them are really molecules. Compounds contain atoms of 2 or more elements bonded together in a specific ratio. They can be broken down into simpler substances, which are elements, by chemical means, but not by physical. So here we have pictorially atoms that are different and bonded together. And all of them in this case are the same. So you've got a solid circle and a unsolid circle. Then in mixtures, contains one or more substances, elements, or compounds that are not bonded together. They can be separated physically, and they retain many of the same properties of its components. So we've got things like salad and Kool-Aid and pizza, air. Here we've got a mixture of the empty circles and the solid circles. Here we have a mixture of, I would bet this is like water because it's got two solid circles and a single open circle. And you've got a solid and an open circle. And here we've got single solids and double opens. So the question down on the bottom, you try. When magnesium metal is burned in the presence of oxygen, magnesium oxide is produced. Is MgO an element, compound, or mixture? It is a compound because it has two different elements bonded together. So feel free to pause the video if you're not done copying all this. The prime time from last time. I received a number of questions on this, and there were a number of students who did not attempt the volume portion, which was a little surprising. But kind of going over the answers, the top one, the volume of the rock, remember this is the volume displacement method, which is what we talked about in the last chapter. So you're subtracting the two volumes here and your sig figs matter. So for here you have a volume of 8.0 mils. The next one you have a volume of the gem being 15.8 mils. For question number 3, your first rock ends up being 3.25 mils, the second rock is 3.75 mils, and the third rock is 8.50 mils. Then I asked you for the first rock, if the length was 2 centimeters and the width was 1 centimeter, what would the height of the rock be? And all of you guys should know that the volume is the length times the width times the height. So you should be able to solve for the height. The height ends up being 1.625 centimeters. If we pay attention to sig figs here, it would be 2 centimeters. Second rock is same thing. You're looking for the height, knowing the length and the width. And then the third rock, I made it a cube. So the lengths are all the same. So the length cubed is equal to 8.50 centimeters cubed. So if you have a cube root button on your calculator, you would be able to find that the length was 2.04 centimeters. So the last question definitely tripped some people up. It says Wendy is curious to learn more about each of her rocks. She takes a few more measurements and discovers that each of her rocks has the same exact density of 3.50 grams per mil. What type of measurements did she take and what were they? Well, she had to have measured the mass in order to get to density. So because she had to measure the density or the mass in order to get to density, you should be able to figure out what the mass was for each of the 3 rocks. Since you know the volume, they say the density is 3.50 grams per mil, you can go ahead and calculate the mass. By the way, that should say grams down here instead of mils. Oh no, that's correct. This is grams. That's correct. Sorry about that. So that was your prime time from last class. That was a little bit of looking back on volume displacement, as well as, do you remember your volumes formula? So the next thing going over was from your yellow packet, pages 13 through 15, reading comprehension questions. Take a look at these. I don't think that there's anything in here that is going to was challenging. One comment that I have is, why is it so easy to float in the Dead Sea? It's because the Dead Sea has a lot of salt in it, much more than just typical salt water. So that increased salt concentration leads to an increased density, which makes it very easy for everyone to float. So pause this and take a look at your answers, and if there's anything that doesn't make sense, please can send that to me via the form at the end. Homework answers from last time. I got a couple of questions. 17.5 was copper compounds often form beautiful blue crystals when a solution of a given copper compound is evaporated slowly. And I was asked, why is that physical? Well, a solution is something that's dissolved in water. So like a salt solution means that salt is dissolved in water. If you let the water evaporate, that is a physical change. The salt is still going to remain behind. So in this case, the copper compound is dissolved in water, and as the water evaporates, you're left with the copper compound. You haven't changed it chemically, you've just evaporated the water. The same thing is true if you leave something sitting out on the table and the water evaporates over a period of time, you'll be left with salt crystals, sugar crystals, or something like that. 17H, the question was bread turns brown when you heat it in the toaster, and that is actually a chemical change because you're basically cooking the things, and the starch inside the bread is no longer able to be returned to its original form. So once you've toasted that bread, there is no way to make that toast look like an original piece of bread. So you've actually chemically changed it. It's been modified, and part of recognizing the different changes, like looking at those 5 clues, in this case, this is an unexpected color change. You wouldn't expect that taking a white piece of bread and adding heat to it is going to cause it to turn brown. That is an expected color change. So that's definitely one way to take a look at that. So I hope the people who ask those questions, I hope that helps. The homework answers from 3.3 and 3.4. Again, pause the video, take a look at these, and see if they make sense. The rest of them. Pages 9 and 10. I did get a question on page 10, number 9A, the bubbling. Why is this not a chemical change? And because that is definitely one of our clues. And the reason for this case is it tells us here that there's water, and there's only water in the test tube. If it didn't tell us that it was clearly water, we would have no way of knowing, and we'd have to assume that it was a chemical change. But since they clearly identify this as being water, we know that it is a physical change, and it's just water evaporating or boiling. Page 11. I got a question about number 6. So why is rusting a chemical change? So rusting, again, is a color change that is totally unexpected and totally irreversible. So if you start out with some shiny silver-like metal, like on a bumper of a car or something that you've left outside, and then eventually it turns into that brownish red color, you don't expect that to happen just because it sat there. And it didn't mix with anything to make it change color. So the only explanation is that there is a chemical reaction that's occurred, so there has been a chemical change. Number 12, about the cooking, the pancakes cooking on the griddle. Again, the way the batter starts and the way the pancake ends up, they have gone through a color change. It's gone brown, and it's totally irreversible and unexpectable. You can't expect that pancake batter that maybe is like just an off-white or a light beige would turn to brown. So it's not like mixing 2 things of different colors like purple or blue and red and getting purple. So that is an unexpected color change. And the panda, I hope you liked the panda. The panda I thought was really cute. I noticed there were a few people who had some of these incorrect because I could tell as I looked at the pictures. So if your panda does not look like this panda and you shaded in some other areas black, or maybe you didn't leave some of these areas white, take a look and make certain that you understand what you might have colored in wrong. So it may still kind of look like a panda, but if this is the correct set of answers. So 13 and 15 should look something like this. One of the questions on your survey was, when water boils, you can see bubbles rising to the surface of the water. What are these bubbles made of? And there were a couple of options for you to choose from. And it was very interesting looking at the answers because every answer was selected by at least one person. And the correct answer is that it's water vapor. So unless you're drinking some water that comes from some really strange place, your water should be basically water. So when the water boils and it turns into a gas, it is still H2O. So the bubbles are actually made of H2O. And so I'm not sure the process of thinking to get some of the other answers, but this is the correct answer. If this doesn't make sense to you, put a note in your survey so I can know what you're thinking, because I don't know how to explain or answer a question if I don't have a question. So if you answered this with something other than D, the water vapor, and you have some thought process that's going on there, share that with me so I know how to respond. Thanks. So our main topics today, we're going to kind of wrap up elements versus compounds, mixtures, and talk about separation techniques. So on page 15 in the blue packet, you filled out this page, and my scanned copy, which was a copy of a printout of a copy, does not have the shading down here that's really clear. So if your shading on your copy does not look like this, take something and shade in these circles so they look very distinct. So for the element, you have single atoms and you have two atoms bonded together. These are diatomic, which means they're two atoms, and we'll talk about diatomic atoms in chapter 4. Compounds, we have a solid circle and an empty circle bonded together. Here we have a solid circle bonded to two empty circles. In solution, there are a couple of different things in here. So here we've got two solid circles and bonded together, and then we have an open and a shaded circle. Here again we have two different things. We have single circles that are shaded, and then we have a diatomic molecule. This mechanical mixture, we have things that are not evenly spaced out, so all the single solid circles are all at the bottom, and then we've got these up at the top. This is actually very much like a micelle or a cellular layer that you would have studied last year, maybe in biology. This is another example where you've got all these things around the outside, and here you have these single empty circles. This is kind of what soap does for us in cleaning. So the big difference between the solution picture and the mechanical mixture picture is the solution, both items or all of the different types of items that are in the solution are kind of evenly spaced throughout. So you can kind of see we've got 4 of these and 4 of those, and they're kind of evenly distributed. Same thing with here, we've got 3 and 3. Whereas the mechanical mixture, things are very different. They're not evenly distributed. So if you think about it, if you were to take a spoonful and you were just going to chop out and take a spoonful out of this mechanical mixture, your spoonful, if you grabbed it from here, would be different than if you grabbed it from here. Same thing true here. Your spoonful from here would look different than if you grabbed it from here. In your solutions, any spoonful you take will be basically the same. They'll look the same. So that's another way of kind of thinking about it. If you took a spoonful of whatever that material was, would that sample that you took be the same as any other sample? So I have a video here, and I really shouldn't show something about food because it's almost dinner time here, but okay.
The world we live in is made of things. Billions and billions of different things, like pickles and pianos, dump trucks and octopi. And even though these things seem totally different, they're all made of the same stuff, just combined in different ways. To give you an idea of how this combining works, let's take something apart. Let's start with this bowl of macaroni salad. If you were to reverse a recipe for macaroni salad, you'll see it's made by mixing together a bunch of ingredients, like macaroni, mayo, vinegar, vegetables, and mustard. This type of combining is called a mixture. When you make a mixture, you're combining two or more things together without actually changing the chemical identity of those things. Like mud, for example. The soil and water in mud haven't actually changed. There's still soil and water. You've just created a mixture of soil and water. Mud. It turns out that macaroni salad is actually a mixture of mixtures, because many of the ingredients, like mayo and mustard, are already mixtures themselves, which is nice for us, because if we look closely, we'll see the three main types of mixtures that exist. The size of the particles in a mixture determines the type of mixture. On one end of the scale is a suspension, like our muddy water example. You get this if you take big chunks of something and mix it with something else, so those chunks are just floating around. Take runny mustard, for example. You'll see a bunch of little particles like mustard seeds, pepper, allspice, and minced shallots all floating around in a liquid, in this case, vinegar and water. This is called a suspension because you've got particles of one thing suspended in another. Now, on the other end of the spectrum is a solution. The particles in this mixture are so small, they are the actual molecules. A solution is sort of like a suspension of molecules, where one type of molecule is blended or dissolved with another. Vinegar is an example of a solution where the molecules of acetic acid are blended with molecules of water. The chemical properties of the molecules haven't changed. They're just evenly mixed together now. Salt water and carbonated soda are both examples of solutions where other molecules are dissolved in water. The last type of mixture is called a colloid, which is somewhere between a suspension and a solution. It's when you take two materials that don't dissolve and you make the particles so small that they can't separate. Mayo is what happens when you take oil and water, which don't mix, and you bind them together, usually with the help of another substance called an emulsifier. In the case of mayo, it's lecithin found in eggs. And now you're left with really small globs of oil hanging out with really small droplets of water. Whipped cream, hairspray, styrofoam, and jello are all other examples of colloids. So let's get back to macaroni salad. You've got colloids like mayo, suspensions like mustard, and solutions like vinegar. But you've also got celery, shallots, and all other vegetable chunks that are also part of the salad. These aren't mixtures really, but we can break them up. Just like a TV can be broken up into smaller and smaller complex component parts. In the case of vegetables, if you keep breaking things up, we'll eventually end with thousands of complex organic molecules, things like ATP synthase and RNA transcriptase and water. So now, once we've unblended all the solutions, unmixed all the colloids, separated all the suspensions, and taken apart all of our vegetables, we've reached the end of what we can unmix physically. What we're left with is a whole bunch of molecules, and these molecules remain chemically the same, whether they are by themselves or thrown together in a salad. If you want to separate these guys even further, we need to unmix things chemically, which means we need to start breaking some bonds.
So there's a couple of very interesting points that he talks about here, where he talks about starting with this macaroni salad and then breaking it down. But I think he does a really good job of explaining the three different types of mixtures. And I think you'll probably find it useful to make some kind of note in your notes about these, because we have solutions, colloids, and suspensions. And they have to do with the size of particle that's inside the mixtures. So draw yourself a little sketch just about these. You're going to see these terms. I'm not necessarily going to be testing you on these, but these you're going to see as time goes on. And I don't know, your book doesn't talk about them in the chapters that we're in, but you definitely will see them and hear about them next year. So I really wanted you to be familiar and have some idea, because some of these terms start cropping into things that you're going to be doing in chemistry. All right, so I hope you liked the little detour into the TED Ed video. So in addition, I want to go ahead and work on some pages in your packet. So we're continuing on, we're on page 16. So on page 16, we've got some pictorial representations of some substances, and we're supposed to identify if it's an atom, an element, a compound, or a mixture. So in this case, these are individual atoms of an element, so it's A. In the second picture, you've got two atoms bonded together, so that becomes a molecule of that element. In this third one, we definitely have a couple of different things in here, so that has got to be a mixture. Number 4, all of these items are the same. They look the same, but they're not all going to be the same element. So this is going to be molecules of a compound. The next one, all of these have, we've got some different things here, so that's got to be a mixture. Number 6 also is a mixture. Number 7 is another mixture. Number 8 is another mixture. And number 9, these all look the same, so that is the atoms of an element. So number 10, describe in words how you can tell the difference between molecules of an element and molecules of a compound. So write down your answer to this. I'm going to take a look at those as I look at your pictures when you submit this page. So moving on to page 17, I'm going to go over a couple of these and then you should pause the video and answer the rest of them. So I typically get some questions on these numbers up here, so I want to go over those. So number 9, brass. Brass is a mixture of different elements, and since brass all looks the same within a brass doorknob, it is actually a homogeneous mixture because it is a mixture of elements and every sample in it looks like every other sample in it. Number 11, air. Well, air is definitely a mixture of different things. We've got nitrogen gas, we've got oxygen gas, we've got trace amounts of some other things, but it is definitely a mixture, and if it wasn't homogeneous, it would all look different to us, or we would struggle to breathe. So air is definitely a homogeneous mixture, and you will see air on some other worksheets and in some other questions, because that's a really commonly asked question for homogeneous and mixtures and elements, compounds, etc. 18 is aspirin. So aspirin, even if you don't know the formula for aspirin, aspirin is actually not a mixture of stuff. It is a compound. It is a single chemical compound, and it's salicylic acid. So it should be letter C, a compound. Then number 26, iron nails. So iron nails, if they're truly just made out of iron, it's just the element. And the same thing is true with other things that we've got a silver tray, a copper wire, an aluminum foil. Those are all intended to just be the element. They're not a mixture of elements. They're not bonded together. They don't appear diatomically. So silver tray is an element, copper wire is an element, and aluminum foil is also an element. So pause the video and go ahead and finish this. And actually, I guess you can't even really tell what this is going to end up being a picture of. But go ahead and color it in. And we're on the last page of your packet. So this one is going to be similar to one of your other punny ones, but now you have elements, compounds, homogeneous mixtures, and heterogeneous mixtures to choose from. So I normally get some questions on 3 and 9. It says 10 here, but it really should be number 9. I was like, why does that not make sense? So sugar water. When you have sugar dissolved in water, if it's truly dissolved well, if you take a sip of it, it's going to taste sweet and it's going to have water in it. And it is a homogeneous mixture. Sand and water, on the other hand, you can try to mix it up, but if you let it sit on the counter for a little while, the sand will settle out to the bottom. It will not stay as a homogeneous mixture. So sand and water, on the other hand, is a heterogeneous mixture. So the sugar will stay in the water and it's homogeneous. The sand will settle out because it doesn't dissolve well and it is so much denser than the water that it ends up settling down to the bottom. So that's one of the things that I always get questions on. So the last section in chapter 3 is about separation techniques. And these are all physical separations for the most part. And your book talks about filtration, distillation, a couple things that are not talked about in your book that are going to be in the short video that we're going to watch in a moment include reverse osmosis, using a centrifuge, and some chromatography. So I'm going to go ahead and get that video going, but I'm also going to turn up my volume a little bit so that hopefully it'll come through. So here we go.
Your cell phone is mainly made of plastics and metals. It's easy to appreciate the inventive process by which those elements are made to add up to something so useful and entertaining. But there's another story we don't hear about as much. How did we get our raw ingredients in the first place from the chaotic tangle of materials that is nature? The answer is a group of clever hacks known as separation techniques. They work by taking advantage of the fundamental properties of things to disentangle them from each other. Simple separation techniques apply to many physical scenarios, like separating cream from milk, extracting water from soil, or even sifting out flecks of gold from river sand. But not all mixtures are so easy to unravel. In some of those cases, we can exploit the differences between physical properties within a mixture, like particle size, density, or boiling point, to extract what's required. Take petroleum, a mixture of different types of hydrocarbons. Some of these are valuable as fuels, and others make good raw materials for generating electric power. To separate them, experts rely on one important feature. Different hydrocarbons boil at different temperatures. During the boiling process, each type vaporizes at a precise point, then gets separately funneled into a container and collected as a liquid as it cools. Separation techniques also take us to the sea. In some drought-stricken countries, the ocean is the only available water source. But of course, humans can't drink salt water. One way to get around this problem is to remove salt from seawater with reverse osmosis, a process that separates water's ingredients by size. A membrane with pores bigger than water particles but smaller than salt particles only lets fresh water pass through, transforming what was once undrinkable into a lifesaver. Meanwhile, in the medical world, blood tests are a vital tool for evaluating a person's health, but doctors typically can't examine blood samples until they've separated the solid blood cells from the liquid plasma they're dissolved in. To do that, a powerful rotational force is exerted on the test tube, causing heavier substances with higher density, like blood cells, to move away from the rotational axis. Meanwhile, lighter substances with lower density, like plasma, move to its center. The tube's contents divide clearly, and the blood cells and liquid plasma can be tested independently. But sometimes, unlike oil, seawater, and blood, the parts of mixtures that we want to separate share the same physical properties. In these cases, the only way to isolate ingredients is by chemical separation, a complex process that relies on unique interactions between components within a mixture and another material. One of these methods is chromatography, a tool forensic scientists use to examine crime scenes. They dissolve gathered evidence in a gas and can monitor and analyze the ingredients as they separate and move at varying speeds due to their unique chemical properties. That information then tells scientists precisely what was present at the scene, often helping to identify the culprit. Separation techniques are not just about industry, infrastructure, medicine, and justice. One of the most technically ambitious projects in human history is a separation technique aimed at answering the fundamental question: what is the universe made of? By accelerating particles to extremely high speeds and smashing them into each other, we can break them into their constituent parts ever so briefly. And if we succeed at that, what's next? Is there a most elementary particle? And if so, what's it made of?
So hopefully you enjoyed that video. So a few notes for you to go ahead and put some explanation about this in your 3.5 notes, because your book only talked about filtration and distillation. So reverse osmosis, their example was showing how they separated the salt from salt water so that the water could be drinkable, and that's used all over the world. There are so many places that have no freshwater sources contained within their country's boundaries, and so, or they're landlocked and there really just isn't a whole lot in the way of lakes. So reverse osmosis is probably the most common thing done in the world today in order to make salt water drinkable. So they put a membrane in there to allow them to essentially, or they're filtering out the salt from the water. But it's not quite filtration. So separating by density, you could let, like their example they talked about was blood. You could let it sit on the counter and wait, but you'd be waiting a really, really long time. So they use a centrifuge to cause it to spin, and that just speeds up the process. So separating by density is no different than other times when we talked about density and letting things separate. Using a centrifuge just speeds that whole process up. And then there's chemical separation, which is chromatography, and we're going to do some examples with that. So you don't need to, other than just note chromatography is another separation technique, and this one is sometimes is a physical separation, other times it is a chemical separation. So we'll talk more about that as we do a couple of our demos and labs. So I am pausing this video recording, and I have a demo that I already recorded using my webcam, and then I will be back. So ladies, this is one of the demos I wanted to do with you if we'd been back at school, so I decided to bring the materials home so I could show it to you anyways. So I've got a bottle here, and there's salt water and isopropyl alcohol. So you can kind of see, hopefully, as I shake the bottle a little bit, that there's truly two different layers of liquid in here. And remember back when we were talking about density, that two different liquids that are not going to mix well, they're going to separate by density. So the denser material is on the bottom, the lighter one is on the top. So what I'm going to do is we're going to put a green marker in here and watch what happens. And this may take a little while, so I'm going to pause the video while we wait for the green ink to dissolve into the liquid. So in order to not have you guys sit here the whole time while we were doing this, we attempted to speed it up by shaking it up, and you can see that the solution is green. We're going to go ahead and take the marker out with a nice magnet, and you can already see the separation of the colors here in the bottle, which is actually pretty cool. Hopefully you can see on the video well that there's a yellow layer at the top, a blue layer at the bottom, and a green layer in the middle. And the green layer is getting smaller and smaller. So this in essence is just like some chromatography that we are going to do in one of our labs. And I'm going to show you a little bit more about this, but this is a pretty neat demo. Now you can clearly see that there are two different layers in this bottle. Let's go ahead and shake it up one more time so you can see it. So it starts out green. And the two different layers separating yellow and blue. All right. So that's our demo for the day. So hopefully you like that salting out demo. That's the first time I've done that. I actually just got that this school year. I thought that was actually pretty neat. So the interesting thing is that with the isopropyl alcohol and the sodium chloride solution, the bottom has the blue layer, and the blue layer is actually in the salt solution because it actually has a higher density. It's about the information has it here, 1.2 grams per mil. And the isopropyl has a density of 0.785 grams per mil. And the yellow color would prefer to be in the alcohol, and the blue color would prefer to be in the water. So we have a couple of things going on with that demo. We had the blue color wanting to be with the water, and the yellow color wanting to be in the alcohol. That has to do with like going to like, and we'll talk more about polarity, or actually you'll talk about that next year. But some things prefer to be in the alcohol, some things prefer to be in the water due to their other chemical characteristics. But we can see the obvious density differences between those two items in there. So that's kind of an example of chromatography where we end up separating the two things based on some color. So we can see there that that color is different. So if we wanted to pull that yellow dye out and do something else with it, we could. So So separation techniques, this is actually one of my favorite sections that I get to do with you ladies, because we have a number of labs that we typically would do at school, and that would include magnetic separation, doing some filtration, evaporation, chromatography, both paper and liquid. And since we're not at school, we're going to do some improvising. So next week, I am planning on having you guys do some chromatography at home, and it will be using items that you commonly have at home. So don't worry, there's nothing you're going to have to go out and buy or anything crazy like that. And I am currently working with the assistance of my husband and daughter, gathering up various things that we have in the house to try to show some different ways of being able to do this lab at home. I think it should go very well. And while we're not together, at least you can do a little bit of lab stuff. So kind of wrapping up for the day. Go ahead and submit your homework onto PowerSchool. You're going to have a number of pages in the blue packet, and I think this wraps up the blue packet. So you have pages 14, 16, 17, and 18. Please submit those in one document. Also, I have another survey on P-Learning for you to submit. I did have a question that was asked in the last survey about how much of the chapter would be on the chapter test, and the answer is all of the chapter is going to be on your chapter test, as well as they will be included on the final, as well as these things carry over into next year. These are actually some of those fundamentals that are just going to continue carrying over. Can you recognize the 5 clues of a chemical reaction? Because next year you'll be given something and you'll be asked to talk about whether it's a chemical reaction or not. So this is kind of a fundamental thing, like learning your element names and symbols. This is kind of part of your foundation. So yes, you will be tested on this, and yes, this material will be on your final. So let me click back. So that was the other question submitted. Homework. So homework due Friday is to do the problems at the end of your chapter. We've got numbers 40 to 46 and 49 to 52, which kind of go over all the material that we've covered in chapter 3. I also am going to post a lab observations of a chemical reaction and ask you to read the background, goals, and materials. If you are unable to print, copy the information from the document onto a sheet of paper or put it into a document that you can fill in and edit. So the data table as well as the 5 questions on a sheet of paper, leaving some space in between them to record your information. So on Friday, I'm looking at doing the thickness of aluminum foil lab with you, so you will need the printout or your written information on a sheet of paper in order to record data as I have the video out. Also, I hope to be doing the observations of a chemical reaction lab at the same time. They're both very, very short labs, and I think that I can be successful at videoing both of them and kind of splicing them together for you to do. And you are going to need pink packet pages 25, 26, and 27 for writing lab reports for these 2 labs over the weekend. So having your pink packet will be very helpful because it has explanations, the rubric, and an example of what we're going to do with your lab report. Regarding your test, there are 2 students who still need to take the test. I am preparing some videos and things for you to watch to review on some of the topics that need to be reviewed, and I still will be discussing answers, improving grades, etc. Part of how that's going to work is going to be depending on when we get back to school together and how that's all going to work. But right now, I don't know how to predict when that's going to happen. So regarding assessments for this chapter, I haven't 100% decided, but I think it's going to be in 2 parts. The first part is you're going to do probably 2 doodle note sheets. One kind of about physical and chemical changes in properties. And the other one will be about elements, compounds, homogeneous mixtures, and heterogeneous mixtures. And the second part will include some type of online test. I'm not too happy with all of the things that I've looked at so far as online testing, and I'm not sure the best way to do that yet. So there will be something. I haven't completely made up my mind on it, but that will be coming. So ladies, I think that was my last, that was my last slide. So ladies, hopefully I've answered some of your questions from last class, and we are wrapping up chapter 3, and I am anticipating getting the packet together for chapter 4 over the weekend. So for those of you who are able to print, anticipate having that to get together over the weekend, as well as if you cannot print, I will be making arrangements to get those to you in some manner. So ladies, miss seeing you. Thank you so much for filling out the surveys and telling me what's going on in your lives. I've been emailing a handful of students when I can, and just kind of checking in with people. So ladies, keep in touch. Keep on hanging in there. You guys are doing a great job. And I will chat with you guys again on Friday. Take care.